the last lecture we studied the kinematics of fluid motion so as to understand the deformation that a fluid element goes through as flow takes place. And we have considered 3 different possible deformations, components of deformation, one of which is a pure solid body rotation. For example, if this is a solid body, you can have pure translation in the x direction or in the y direction. This is one form of motion that a fluid element goes through, and in the case of pure translation in any direction, the fluid element does not get any deformation, it remains the same. You can have pure rotation along the diagonal of this, and here again we can see that the shape does not change, there is no noticeable deformation in this. But we can also have a pure stretching, so that the volume, it becomes elongated in this direction or it becomes elongated in this direction, and there can be a change in the cross sectional area, and there can be a change in the shape from an initial rectangular thing into more rhombus like thing or a general quadrilateral like thing. So these are different kinds of deformations that are possible, and we have seen that the rates of this deformation can be expressed in terms of velocity gradients, in terms of linear combinations of velocity gradients. And this is an important aspect, because it means that in the general 3-dimensional case, all the 9 velocity gradients, so that is dou u by dou x, dou u by dou y, dou u by dou z, and similarly for the 3 v components and the 3 w components, all the 9 velocity gradients metrics together can define the general rate of deformation that is possible for a fluid element. And we would like to relate this rate of deformation in a linear way to the stress that is induced by relative motion. And so that the idea would be that the stresses that are present in the conservation of linear momentum can be replaced by these velocity gradients, and since the velocity components are already part of the variables, we can then replace the stresses by velocities and thereby create a system of equations which is closed, in the sense that we have as many equations as there are the number of variables. So to this extent, in the last class we decompose the stress tensor into a hydrostatic component and a viscous stress component, which arises only because of relative motion. The hydrostatic component is present, this pressure is compressible, is present even when there is no relative motion, whereas this is supposed to be present only when there is relative motion. And given that a relative motion produces strains, okay, strain rate, which is given by dou u by dou u k by dou x m in the general case. So this can be written as dou u by dou x, dou u by dou y, dou u by dou z, and similarly dou v by dou x, dou v by dou y, dou v by dou z, and dou w by dou x. These are the 9 components that are appearing here, and together this is the strain rate components, and the idea of putting it here is to make a proportional relation between the stresses that are induced by relative motion and the strain rates that are a result of relative motion. We note that the distortion of the rectangular element is possible only when the four corners of this, the ABCDs, have different velocities. If they have the same velocities, then they are just translating in a certain direction without any distortion. When there is relative motion within the fluid element, within the fluid continuum, when ABCD have different velocities, then there is relative motion, and that relative motion is present in the form of non-zero velocity gradient components here, and these give rise to different deformations, like we have mentioned that delta alpha plus delta the rate of deformation is given by delta beta and the average of these two, and this is expressed as half of dou u by dou y minus dou v by dou x, and so on like this. Okay, so this is the shear rate, and this is expressed in this particular form here, perhaps with a negative sign here. And so this is a linear combination of two elements that are coming here, dou u by dou y and dou v by dou x. So we are now saying that we are seeking a relation, a linear relation between tau ij and epsilon km. This is a hypothesis. And why are we seeking a linear relation? Because a linear relation is the simplest possible that we can have, other than having no relation at all. If it is a nonlinear variation, then it means that there will be this plus some multiplication of this, and that involves additional constants and so on. So this is the simplest possible, and the simplest possible appears to work for very common fluids like air and water. Okay, so that is the advantage of this. The simplest common fluids that we can come across obey empirically, based on empirical observation, we can say that they obey this hypothesis, and which is therefore this hypothesis is very useful practically. But there are a number of other common fluids, more complicated fluids like blood, which contains lots of white corpuscles and red corpuscles and those kind of additional things which do not obey this, this linear hypothesis. Similarly, many polymeric liquids which have elongated oriented molecular structure with long chain molecules do not obey this, this particular assumption. But this is a very useful assumption, and it is an empirical hypothesis. It is a hypothesis which is backed by empirical observations of the goodness of this hypothesis. So with this thing, we would like to have a mathematical formulation for this, so that we can rewrite this tau ij in terms of this deformation strain rate tensor involving the velocity gradients, so that if you substitute this into this, then the stresses would disappear and you will only have velocity gradients, and the velocity gradients are not new variables. So in that sense, that is where we are heading. And we mentioned that this is a tensor and this is a tensor. A general relation would have a ij km epsilon km, okay, and this is a 9 by 9 matrix. And so that, and we also mentioned that this is, these are material properties, okay, like viscosity that we are familiar with. But this many material properties are very difficult to get empirically, and we also would like to study this particular thing further and take advantage of special features of the matrices that we are trying to relate. And what are the special features? We know from angular momentum that tau ij is symmetric. Okay, so that means that there are only 6 independent components. And in the special case where we do some matrix operations and rotate this and then write this in the principal coordinate system, then we will only have tau AA, tau BB and tau CC, and all these things are 0. So that is, we can this is in the general case of x and y directions, and when we do principal component analysis and we put this in a diagonal form, then we will have non-zero components in the shear stresses and only normal stresses. So this is a special coordinate system aligned not in the ij but in the a principal coordinate direction here, and here we have only three normal stress components. Only three non-zero normal stresses. Okay, and so that means that here in this special thing which we are doing by matrix multiplication of matrix operations on this, so that we are not introducing any new features into this, we are looking at 3 independent components here. So instead of 6 independent components, we have 3 independent components. And similarly, the epsilon here Km is dou u k by dou x m, and in general this is not symmetric because it is not necessary that dou u by dou y is the same as dou v by dou x and that. But when we look at our objective is not to take a relation between this and this, but to seek a relation, linear relation between stress and the deformation rate tensor. Okay. Now we have said earlier that if there is a pure solid body rotation here, the shape remains always rectangular and there is no deformation in this. So you could say that pure solid body rotation does not give rise to any change of shape, it does not deform the rectangular element. Similarly, pure translation will not deform this. So the only thing that is actually changing the shape and thereby creating a strain on this is the shear strain rate and the extensional strain rate. Okay. So the shear strain rate is expressed as half dou u I by dou x j plus dou u j by dou x I. Okay, in the general case, and we can see that this is symmetric, and extensional strain rate is dou u k by dou x k. So that is dou u by dou x, dou v by dou y, dou v by dou z, and those are these components here. And shear strain rate has this plus this going together, and this plus this going together, and this plus this going together. So the same component, it's a summation of summation of these two and summation of these two and summation of these two. So that means that a combination of these two, the deformation rate tensor dij is symmetric. Okay. So if dij is symmetric, then this is also has 6 independent components. Now this also can be decomposed into the principal components. Into this can also be rotated, and so that we have only d dpp, dqq and drr. All the others are 0 here. Okay. So, we are looking at essentially a matrix rotation operation in such a way that a general tensor with all the 9 components are converted into a special orientation in which only the diagonal elements are non-zero and all the others are 0. So, this means that now we have a set of coordinate axes in which we have only 3 stress components and another set of coordinate axes in which only 3 non-zero components of the strain rate deformation rate tensor, and we would like to have a relation between this tau ij versus d prime km, where these are these specially rotated operations here. Now, when you are seeking a relation between these two which is linear, then it is necessary that the principal coordinates of these and the principal coordinates of these are the same. So, principal axes of both must be aligned. If these are not aligned, then you cannot have a linear relation. So, that means that we can now say that we are seeking a relation between not 9 by 9 components, not even 6 by 6 components. We can only have, if we say that we are going to have a linear relation between this and this, mathematically you can only have 3 independent components here and 3 independent components here. Okay. So, that means that you can only have 9 independent values which will describe this general relation which is applicable in any coordinate system, but the same constants must also be applicable in the principal axis coordinate system here. Okay. So, in that sense we have only 9 independent components. And what are these 9 independent components? We can put these as sigma tau 11, tau 22, tau 33, because only diagonal terms are there, and similarly d11, d22 and d33. Okay. Now, what kind of generic linear relation that is possible? So, we can write, for example, tau 11 is equal to a1 times d11 plus a2 times d22 plus a3 times d33. Okay. So, this is for different values of a1 and a2, a3 which are constants. We have a linear relation in which tau 11 is expressed as a linear combination of all the 3 possible variables on the right hand side. So, when you have all the 3 variables on the right hand side figuring here, then that is the most generic relation that is possible. If you put d1 times d2, then that becomes maybe that is not a linear relation there. Okay. Similarly, we can say that tau 22 is also related only to the same d1, d2, d3, but using a different set of constants. For example, a4 d11 plus a5 d22 plus a6 d33, and tau 33 is also written in terms of the same things. So, you have a7 d11 plus a8 d22 plus a9 d33. So, here we have 9 constants a1 to a9 which define a general linear relation between the 3 rotated stress components and the 3 deformation strain rate components. Okay. So, now these you cannot reduce it further without assumptions. So, here we make one more assumption which is that the fluid is isotropic. So, when we say the fluid is isotropic, then what we are saying is that application of a force on this produces a deformation in a solid body, and in a case of a fluid it produces a rate of deformation. Okay. And what we are saying is that if you apply as a tensile stress in this direction, then in a solid body it produces a deformation in this direction, and also in the z direction. Okay. So, in an isotropic medium it does not matter whether you apply the tensile stress here and here, or in this direction or in this direction, the response of the surface is the same in all directions. So, that means that if you apply tensile force here, then the body elongates here, and then it also contracts on this side and contracts on this side. The contraction along this side, the z direction, must be the same as the contraction in the y direction. And similarly, if you now apply the stress in this direction, along the direction which you applied the stress, you have a certain extension, stretching, and in the other two directions there is a small contraction. And so, the contraction that is produced by the application of a stress in this direction, in the z direction, so that is you apply a stress in the y direction, that is a tensile stress, it produces a contraction in the z direction. Now, similarly you apply the same stress, same tensile stress along the x direction, it again produces a contraction in the z direction. If the body is isotropic, it does not matter whether the contraction is produced by application of a tensile stress in the y direction or x direction. If the stress is the same, then it produces the same amount of contraction in the z direction. Okay. Similarly, if you apply in the z direction a certain tensile stress or a compressive stress, and that produces a corresponding deformation in the transverse direction, then the amount of deformation that takes place, that is produced, must be the same if the same tensile or compressive stress is applied in the other direction. So, in the other orthogonal direction. So, what we are saying is that in an isotropic medium, we are allowed to distinguish between a deformation which is produced in the direction of application of the stress and a deformation which is produced in the transverse direction. In the transverse direction, you cannot distinguish between y and z. Okay. So, there can be one deformation which is in the direction of the stress, and there is the same deformation which is produced by the same amount of stress in the other two directions. The two transverse directions are similar. So, that is the idea that we can take it here, and that kind of deformation, that kind of meaning can be rewritten in this way, that is tau 11 is B1 times D11 plus D22 plus D33 plus B2 times D11. Tau 22 is B1 times D11 plus D22 plus D33 plus B2 times D22. Tau 33 is B1 times D11 plus D22 plus D33 plus B2 times D33. Now, you look at this relation here. In this relation here, it is possible for tau 11, tau 22 and tau 33 to be different, because although they are related to the same set of variables on the right hand side, D11, D22, D33 here, even though for a given set of values of d11, d22 and d23 this contribution is the same, there is also a contribution coming from this. So tau 11, these three stresses will be equal only if these three are equal. Okay? If these three are different, then you can have different stresses that are possible. So this is a generic description of a linear relation between the principal stress components and the principal deformation rate tensor components involving only two constants, B1 and B2, okay, and which is isotropic because you have a deformation d11 associated in the direction of stress, and you have something like a transverse component which is coming here. Okay. So in that sense, this is a relation between the same three components on the left hand side and the same three components on the right hand side, which is written with only two independent constants, and this kind of relation is applicable for an isotropic medium. Okay. So now what we are saying is that this linear relation between a symmetric stress tensor and a symmetric deformation rate tensor here for an isotropic medium would have only two independent constants, and normally we put this as lambda here and this as mu. This is our dynamic viscosity, and this is known as the second coefficient of viscosity, and this relation expressed in the principal coordinates will be like this, but when it is transformed from the principal coordinates into general ij coordinates can be written as tau ij equal to mu dou u I by dou xj plus dou uj by dou xi plus lambda times dou uk by dou xk. This is a relation between the stress induced by the relative motion and the strain rates, deformation strain rates that are induced by the stresses, and that relation is linear and it is for an isotropic medium involving the two coefficients mu and lambda here, and so delta ij here, okay, the Kronecker delta function. So this is the expression that we have. Here usually this particular thing dou uk by dou xk is very small for most fluids, so this becomes negligible, and so we do not need to really know the value of lambda in most cases. So this can be obtained for some simple gas species as having certain value, but otherwise this is not possible to, it is not possible to get an accurate estimate for this, whereas viscosity is something that can be measured in the special cases of where we impose a velocity gradient by rotation between two cylinders and so on, we can get an estimation for velocity. So this is easily measured. So we measure the viscosity and then we make use of this relation here. So this relation now can be substituted into this, and that gives us minus p delta ij plus mu times this and lambda times this. And what we then have is that the stresses on this side are expressed in terms of pressure and velocity gradients. So velocity gradients are not new variables, and material properties, which are the two viscosity coefficients, the first coefficient of viscosity and the second coefficient of viscosity. So in the next lecture we will see how, when these are substituted into the governing equation, we will end up with a conservation of linear momentum which has only extra variable as a pressure. Okay. So that the 3 momentum equations for the 3 velocity components plus the continuity equation together constitute a set of 4 equations. Thank you.